I felt.
I don't need the volume on. Then that. I can't. Like you can see it on my laptop, but you can't see. It's really dark for some reason. Oh no, I don't.
It's dark. Is there a cat on?
Mm-mm.
Yeah.
I think it might just be the lighting in here is weird.
It just tries to think that. The new camera? Apparently, yeah, it is new.
I don't know why it's doing that.
Okay. It's too smart. So I thought maybe.
But then you cover up half the thing.
Like, yeah.
I mean, you can see it on here. I can see you. I just don't know what you can't see it on the wall like at all.
That's a oh. Do you think it is recording in the right?
Let me make sure it's recording.
Or it's
Yeah, it's recording.
like you'll be able to read it? Maybe pick up one of this as your thumb. Oh, is it? On this one.
I think it should be visible.
We will take it out. On that. Just bring it for you. On each.
Oh no, anytime weird.
For some reason, it flips this way instead of this way. Oh, yeah, that's my printer problem. Oh, I didn't check on that. Okay.
You just need. I think you need to just adjust your print settings.
I know, I tried all of that.
Every time he printed something over the semester, it would do that, or over the summer. Like he would scan my like thesis notes, and then he'd return them, and I had to write a code that would take in the file, turn every other page, and spit back out the file.
You at least have the, I print it out and then I have to do this. Yeah, we have to place right now, we in the back page. But I won't be printing most of the time, so you don't have to deal with that. Okay.
Oh, because I got a syllabus and not syllabus pack. Whoa.
So this should be. This is. Map stuff.
Yeah, you can read the board on here, so it's just going to be dark for some reason.
Make sure you're in the right place. I think many of you I recognize. Some of us are at least new to each other. So maybe just go around. All of you get 3 sheets? Make sure you fix that up. And first few minutes, at least we can know the names. That is all that.
Okay, my name is Ken Parks. I'm a master's in math student. I did my undergraduate here and bachelor's of math and chemistry.
Hi, I'm Sanya. I'm studying as a PhD student this semester with the Doctors of Europe.
Good. Hi everybody. My name is Deepak and I'm from Nepal. I did master's in physics and I'm doing my master's in physics.
Jackson, I'm a master's student for math and physics.
My name's Thane. I'm doing my master's with Dr. Mizuno in physics.
My name is Rocky. I am doing my master's in here with Dr. Bamsu.
I'm Pooja, here I'm doing physics master's graduation and I'll be back.
Hi, I'm Pradeep. I'm doing PhD with Sensor. Kadish. Nice. And yeah. Thank you. Okay, so. We have to study something here, mostly. I'll start with. How far does it go? It goes all the way here.
Where you had your hand, like 2 more inches,
Okay,
that's where it stops.
thanks. What do you expect in a course on mathematical methods, since there are 2 of you from a math background? In general, all of you can say, but anything particular you want to say? What do you expect in this course? Yeah, understand. Oh, I'm sorry. Okay, any comments? Yeah, Jack?
Just from previous experience, like the dyadics and index notation and all that sort of stuff, getting more comfortable with that at least. Tensor notation, some tensor algebra stuff like that.
Yeah, so is that familiar, the words Jackson used, index notation and dyadic notation? Both of it is at least used by me a lot, but I think in general, since I'm from a physics background, it's used by most of the physicists. That's common, it's corrective. And we will begin with that. So we will begin with index notation. Maybe very quickly I can write down what we can expect. So index, it's readable to everyone. The back. I know I write small. Who's that?
Yeah.
So index notation, we will see if that is not, if you don't know the details, don't worry about it. And I'll include dyadic notation also in the same. So these are ways to deal with when you're doing vector calculus. You might be familiar with this operation. That's a generalization of derivative in 3 dimensions. If you're familiar with the first derivative in position, this is a derivative with position in 3 dimensions. And when you operate it on a vector, that's one of the nicest, the simplest vector you can think of is a position vector, the coordinate itself of an object, and one has to evaluate that. And then you get identities, very convenient identities like this. So you want to get used to this. So right hand side is a dyadic, these are vectors. So we want to introduce what this means. So we will learn what how to use this. Where is this used? If you're doing any serious electrodynamics, vector calculus is there in every equation of it. Maxwell's equations are written. Very convenient when you use this. And then once you get the algebraic rules for that, you just operate it through. Having said that, when you have a collection of a lot of rules, it does get intuitive, and if it is let's say algebraically tedious, then these intuitions just help through in your calculations. But to me, at least, it seems to me that these are just a set of rules, nothing conceptually deep in there. We will do that. We will begin with this. In the same spirit, we will also try to do curvilinear coordinates. We always tend to think in terms of I hat, j hat, and then k hat coming out of the board, but that is not necessarily the uh, most convenient coordinate system or basis that you have. Another one is spherical coordinates, right? I will only write them down. So this is r hat, eta hat, and phi hat. So these are spherical coordinates, and we want to be able to work in that and at least have a simple formalism where we can develop things there. So we'll do that. Next, we will jump into what is called complex numbers, or we will go further and say complex analysis. It's good to think of complex numbers. How many of you have not seen? No, usually no one likes to say they are not seen. How many of you have seen complex numbers? Okay, most of you, right? At least a little bit details. So, what is the difference between a complex plane and a real, let's say, x and y? That is a ij plane, xy plane, and a complex plane. Any difference you can think of?
Funky integers.
As what?
Funky integers.
Funky integers. Yeah, that's probably two. Yeah, you have something in mind. Yeah. Mention that again when we are doing that. Yeah, I don't get it. So, but again, any difference between a complex plane and a real plane, or is it the same? I think of them. Like if you're familiar with complex numbers, you say this is like z is equal to x plus I, where I is, what is I square is equal to -1, maybe, right? And this is x, and that's y, right? And real numbers will be, again, you say this is x and y, at least in rectangular coordinates. You say this is r is equal to x. This is I hat plus yj hat. Where there is this rules, let's say that I hat is 1, I hat, j hat is equal to 0, and that's j hat. So it seems, especially when you do most of the algebra, if you're doing addition of vectors, addition of complex numbers, there is a lot of similarity. The product is differently defined here. Here you will define vectors. So this is two real numbers. You will have a scalar product or a vector product. Here you will have a product of complex numbers. The definition of product is entirely different. And division is not defined in here. You usually do not define a division of a vector, right? 1 over a vector, that's not that. Even then, you would say, at least algebraically, there is a lot of similarity, but geometrically, there is a significant difference in the sense that here, when you think about infinity, so this is as you grow farther and farther, you reach points that are farther and farther from the origin. And each point there is unique, like you expect. So, right, if you're in the universe, if you're on one side of the universe and on the east direction, and another side of the universe on the west direction, you expect to reach entirely different places. But that's not the case in complex numbers. Infinity is a point in complex number, even though it's a plane, the whole point, the whole surface where you go far is really one point. In what sense is it a point? We will emphasize that as we read. The main point is that however you approach a point, the property of the function is exactly the same. So that will be an important property that we will use to study the properties of the functions on a complex domain. But that will be the central point there, that the infinity point is a single point in the sense that however you approach it, you approach similar features of the function. So we will start from there. So basically, this involves what is called an analytic function, which is a property associated with on a complex plane, not on a real plane. And once you have that, you have a lot of nice properties. You can do various integrals, which are sort of not possible to do in normal ways, but you can do it using complex integration. So we'll have nice applications also. Once we go there, we will come back and do special functions. So we will do Fourier eigenfunctions. Let me just say Fourier function. It's just a Fourier, yeah. I like to call it, this is not a standard usage. Fourier. Yeah, but here in physics, quantum mechanics, this is very common. So you would say this is Fourier eigen functions. We will introduce Legendre eigen functions and spherical eigenfunctions and Bessel. So these are the four eigenfunctions we will talk about, and we will talk all this in the context of a very generic technique, which will be called Green's function. What is a Green's function? Anyone? Green's function, let's think of it like this. Maybe let's start with a differential equation plus omega square. What's the solution to that equation? It's written in a slightly different way, but all of you are familiar with that. Try to rewrite it in some form and you will be very.
A cosine omega plus B sine omega.
Yeah, that's the equation of a harmonic oscillator. If you have a spring and a mass connected to each other, and if this was a time variable, that's the differential equation you will get. And the solutions for this are f of x is equal to a cosine omega x plus b sine omega x, where a and b are determined by initial conditions, but here if it is x, then it should be boundary conditions. So that's a normal differential equation. This will be a homogeneous differential equation. Homogeneous in the sense that it is zero on the right side. We can immediately ask what would be the equation if this was c of x. That's another function. So now it has become an inhomogeneous differential equation. A technique for solving for these equations, if we know the solutions of the homogeneous equation, is what is called a Green's function. So what's a Green's function? Of this problem, we will try to solve the right side having a very special function. This will be called a delta function. We will introduce all this. And if we can solve the second equation, which is called the Green's function, we can solve the first equation for any right hand side. Give me any right hand side. If I know how to solve for f of x, when it is 0, let's solve this 0. When c is 0, that will be the Green's function. Where do you see a Green's function in real application? A point charge. If you do not have a charge, that means the right side is 0. If you have a point charge, that's a that's like a delta function. So if you want an intuition for a Green's function, you already know it. The electric potential due to a point charge is a Green's function in the Maxwell equations. So you're very familiar with Green's function in many ways. So we will try to connect those things. So that's very broadly what we will do. You have to reach that. Often I have to compromise on one of these functions because you get slower as you proceed and you spend more time in one of these things. And usually I have done either I compromise spherical harmonics or Bessel functions, either one of them is compromised. But at this point, since you're on the first day, I'll say we should try to cover everything. It can be ambitious, so we'll see. Okay. Any comments from your outside? Feel free to ask questions anytime. Oh, I had to go through the syllabus too, right? Yeah. Perfect. The class meetings, it's on Mondays and Fridays. Office hours is right after this lecture and at 3 o'clock in the afternoon also. Usually a good question comes up and that is regarding references, textbook. There are two textbooks I have, let me not call it textbooks, references, that's a better usage in here. The first one is Methods of Theoretical Physics, and the second is actually both sound the same, Methods for Physicists. One is by Erskine and the other is by Morse and Feshbach. If you really do not want to spend any money, I'll never ask you whether you have a textbook or not. It's all up to you. Often I see students surviving based on my notes alone, but I wouldn't recommend that. That's not my advice, but students tend to do that. I have nothing against it. But if you really want to learn something from the literature that is already there, where I filter out and present it in a short, brief way. The first reference is very comprehensive. If you want to invest on a textbook that will last you for more than 10 years, that's the textbook. Morse and Feshbach it's a classic in mathematical methods. But having said that, it is hard to read. It is not the easiest textbook, but content-wise, very, very well written. There is probably no mistakes. It's almost if you have it in this textbook, then that's an authority. So first textbook is an authority, but harder to read. The second textbook is easier to read, but not necessarily the most comprehensive. You might even have mistakes in there, but not necessarily mistakes that will affect this classroom. We should all be very comfortable with using Erskine, and you should not see any issues with the mistakes I'm talking about. But at some deep level, there might be issues in that. So is that a reasonable way of presenting the two books? So if you want to invest money for 10 years, then use the first one. But if it is just for a semester, then I suggest the second one. And if you don't buy any book, if you use some resource from the internet or anywhere, that's I don't care how you proceed. This is my recommendation for this. Any questions on that? Let's go. There will be a course web page. So most of what we will need in the course will be available on the course web page. It is not SIU owned web page. It's a personal web page, but at graduate level, I have never had any issues from anyone saying this. So yeah, so that's the page. What do I mean by it's a course web page, homework, lecture notes from the past, and whatever content we have from the past semesters. I have taught this course probably 4 or 5 times in the past, so you will have all the materials, including the exam, homework, everything from the past courses on this web page. So there will be a link. So just go around. It's a good bit of stuff. So, but at the same time, it is not too much stuff. If you spend about half an hour, you will know all at least what is what are the things available in there. Generally, at least what I tend to do is that a something that I have asked in a midterm exam becomes a homework in the next year. So, for example, I have to give you a midterm in the end of September. I try to come up with at least one new problem, and that's a new problem in this semester. But in the next semester, it becomes a homework. So if you go around and look into, especially there are recordings these days, at least some of them semesters have recording. If you go to the recordings, you might get solutions for the homework problems in the lectures. Having said that, it's not easy to search a recording. So my recommendation is when you have a homework, work on your own, at least for half an hour, think about it. And after that, start discussing. It is okay to talk to each other about the homework. It's okay to look into each other's work as far as homework is concerned. And only thing I ask you to do is that have your own writing. When you submit, it should be yours. But you can look into others' work, your colleagues' work. If you're not comfortable with talking to your colleagues, come to me. So feel comfortable to ask. Usually, at least what I've seen is that sometimes the notation is what is a stumbling block. If I just tell you what I mean in the first few sentences in the problem, that itself might help you proceed a lot. So feel comfortable to ask, come and talk to me. Otherwise, at least talk to each other, because most of the time people are more comfortable talking to peers. So that's and as we go, it might get clearer. And some of you have taken my course before. It's the same strategy I go with, but at least those who are new, please, if you don't get the logistics of the course within 1 week, talk to me. Like at least think to me. Tell again, brother. Help me, yeah.
If anybody get a problem, then we can help further.
Yeah.
It's easy, we can just go to the link and then find everything.
Perfect. Is that helpful? Okay. There are 2 exams and 1 final exam, but there is one thing important, and that is quizzes. This is 10% of the course. But unlike, and maybe I should say homework also, homework is 30% of the course. This is about once in a week, once per week, right? And this is once per lecture. But even then, there is a significant difference. Maybe I should also say exam, midterm is 15 plus. No, that's not. 20 plus 15. And the final exam is 20. This will be in class. the midterm exam and final exam will be very similar to homework. The main difference is that in the homework, you're allowed to talk to each other. You can use any resource you want. You can use the whole of internet there, but here you will have to do it on your own. But then I ask a little smaller questions because homework questions typically take a long. They are significantly longer. They are deeper, maybe you can say. But I take a small piece out of it and ask in the one. Homework is available on the course webpage. It will be like the first homework I have printed and given to you, but next time I won't give it to you. You go to the web page and download it yourself.
That comes every Monday.
It's once in a week, approximately once in a week. Okay, so this will keep changing. Ideally, yes, every Monday. Like today, I have one second one, so ideally it should be that. But what happens is that typically we get slowed down. Like I might not be able to finish content. I slow down, and then the homework shifts. So that's all it will go. So ideally, yes, but it won't. This is approximately once in a week. It is not very periodic, right? So keep a watch on it. I will write down the due dates for that. What I was emphasizing here is that it is a typeset homework. It is very clear. Instructions are very clear in a homework, but quizzes will be very different. Quizzes will not have a written format. They won't be written at all. While during a lecture, I randomly come with random question. It's really random in the sense that I don't come prepared. It comes out of the discussions. And or while I'm talking, I feel that, oh, that should be something that you should look up. So I might just say that, like a classic example I can give is what is the radius of our universe, right? So this is a random question, not even related to a course, and I can give that as a quiz. Now, notice the quiz is not written down. You have to write the question. You have to phrase the question, and think of a reasonable answer. Since the question is not necessarily a reasonable question, don't spend more than 5 to 10 minutes on it. If you want, you can. That's the whole point, that you should think about it, you should ponder on it, but not for the scores. On your own, you can, but for the course, for the grades, don't spend more than 5 to 10 minutes. So quizzes will not have a written format. You have to decipher what the question is and write it down. And in the before the next lecture, like today's Monday, next we meet on Friday. Before Friday, you have to submit it online. This is slightly different from those who have taken courses with me. I usually ask you to submit it in class. So submit it online on D2L. So just scan it before the lecture and it just goes in there. That just
for the homework also?
No, homework I will ask you. So homework is by hand. Right? This is manual submission. Manual submission. Is that clear what I mean by manual submission? You write it on a paper and bring it to me. And this is digital. This is on D2L. Is everyone familiar with what D2L is? A new D2L? No?
Yeah, little bit.
Little bit, okay. If by Friday you're not able to, ask me. And those who are new, the first homework and quiz, you can have a little leniency, right? But only in the first, and not for others. Or if you guys get late, I mean, others have to be playing, they will lose the points. So make sure that those who are new, they are all able to submit. It's not a serious thing I'm saying, but try to help those who are. But it's not really hard. D2L, just go. Okay. What was I saying? Yeah. So quizzes are not phrased clearly. There might be more than one question during a lecture. Sometimes I've noticed it can go as high as 5 also, but don't spend too much time. Think about it, and maybe others can tell how much time does it take to do a quiz. Believe
10-15 minutes.
so 10-15 minutes. So don't, and I don't expect you to spend more than 10-15 minutes. Like radius of the universe, you can spend sufficient time on it, but it's really not probably constructive or productive if you really spend 5 hours on it, at least for this course. It might be useful for your own thought process, but it's different.
I remember we in the classical mechanics for that question.
Oh, it was the same question, really? Okay, so maybe I should ask not radius. What's the age of the universe? So instead of radius, make it age of the universe. And is it connected at all or not? Is the age and radius connected? Maybe yes. Okay. Quizzes add a little more to it. Now, at the end of the semester, you have 100 points. Like hopefully this adds up to 100. Right? No, more than 100. And let us say that one of us gets 60 out of 100. So so this is the total. This comes up to 60. But then what I do is I start with 60 and I try to return back the points that you have lost. If I return back all the points that you have lost, that would be 100 minus 60, then you get full points. Every one of you will get full point. But that will be not a good assessment. So I give you a fraction of this. Well, let's say this is A. So this is usually this is about, let's say, 0.2. So that's 20%. So I say that maybe, and how do I decide on that? Based on my own assessment, maybe the questions came out hard. If it was easy, then I will not give you any points. I usually don't give you negative points. That's not reasonable. So I don't do it. There's nothing unreasonable about it. But often 10 to 20% giving is normal. So I give back if it is so 2 points into 4, so 8 points you get back with 60. But then there is also one more parameter, and that's y. And this is what you get in here, right? So for example, in quizzes, if you got 10 out of 10, this will be your y. So let's say if you got 9, let's say. So that will be your y, right? So this will be 0.9. So if you happen to not submit any quizzes, so you got 0 in the quizzes, then you don't get anything from what I returned back. So in that sense, quizzes are important. So from my perspective as an instructor, I use quiz as a way of how much you're participating in the course. So that's my way of doing that. So that's 0.9. So how much does this come out to? So if you have 60, so this comes out to 60 plus 0.9 times 0.2 times 40. So 8 into 9, so that's 7.2. So this is 67.2. Right. So two significant digits. It's about 60. 70. Is that clear? So notice quizzes are important. So don't ignore them. It is easy to ignore it, but then somewhere it might play important role. In the past, I've noticed that most of you get 10 out of 10 in quizzes. That's fine. Experience in the past, so don't lose any points. If you are absent and if you have good enough reason, I will excuse it, but it should be an excusable reason. Don't. If I see that it's being misused, I will change the rules. For now, usually it is never a problem. So if you have a good enough reason, just tell me. that's all I can think of. Anything else you can think of? Any questions? About the syllabus? Was that helpful? Let's do. Okay. So let's study something for the homework. So we'll start with index
Yeah, that's good.
notation. Okay. So let's start with what are vectors. Vectors. What is the vector?
That just gives you the direction.
Something with a direction, right? So yeah, so often we will write, so this is a vector, yeah, so that's a vector, so this is a vector, right? That's a direction, right? So and it doesn't have to be really a position vector, it could be force, it could be angular momentum, so those are all quantities that are vectors. Again, there is a length associated with it, so there is a length associated with it, and there is a direction associated with it. So, yeah. In 2 dimensions, so in 2 dimensions, if I were to draw a vector like this, that's my vector. I again have a length, which let's say there is a length. And by direction, if I want to make it more quantitative, I have to have another line. If I have to specify a direction, it's in reference to something, right? So there is a reference line and there is an angle. So there is angle 1, let's call it. Right. In 3 dimensions, immediately you would have, this is your vector again. Now, when I have to specify the direction, I need to have the angle specified with respect to at least 2 lines, right? Usually, for example, if you're sitting on the surface of Earth, you will have a latitude and a longitude. Those are directions, right? So there's an angle with respect to the azimuth. I think, yeah, azimuth and what's the other vector called? No, zenith. Zenith, yeah, I think it's one is the zenith and the other is what are the names for theta and phi? Spherical coordinates quiz, right? We have quizzes, right? And so there is theta and phi, so straight line, and then there is angle 1 and angle 2. What are these called in spherical coordinates? Nomenclature. And spherical. So you get the spirit of what a quiz will be. So these are the simple questions in quizzes, which is this is at this stage just a nomenclature. Sometimes it can be deeper questions also. If I were to draw this in spherical coordinates, so this will be z hat. Let's say this is z direction, and that's your x, that's y, and in parallel, that's my angle theta. That's 90 degrees. And with respect to x, this is my phi. Usually in mathematics, textbooks in mathematics, they interchange this angle theta and phi. It's reasonably consistent. Most of the physics textbooks use the angle with respect to z as angle theta. But in mathematics, it is the angle phi that comes in. But once you know it, just make sure that the literature using that is using the right variable that you're used to. So this could be a vector A. So that's an intuitive way of looking at vector. That is a length and two angles. Right? But this is not the most convenient way when you're doing calculations because they do not obey simple algebra. Like angles don't add nicely. Length doesn't add nicely. So they don't obey 2 + 3 = 5. Like the normal addition that we know is not respected by the length and the angle. So it is convenient to go to some other variables, and that is the projection of these vectors in orthogonal directions. So for example, this is your two directions. So if this is your vector A, this will be A1 and that will be A2. They are projections of a vector on orthogonal direction. So in this case, this will be A1. That makes sense. That's your A1. This is your A2. And that's your A3. Let's work in 2 dimensions so that we have clarity on this. But expected that we should be able to deal with 3 directions, 3 dimensions too, and we will deal with that. Okay, so a vector A geometrically is that in 2 dimensions, it will look like this. For A, so that's the angle phi. This is A1, that's A2. And the length of this vector is just the vector itself without the vector sign on it. So often we will say vector A is equal to, or maybe I should first give you the geometrical idea here. So this is A1, this is A2, so it's clear that A squared will be A1 squared plus A2 squared. And the angle phi would be equal or tangent. And also A1 is equal to A times the sine of phi. 2. So just from this, these are triangle properties, right? If you take this triangle, all of this comes out. Cosine phi is adjacent over the hypotenuse, sine phi is opposite over the hypotenuse, tangent phi is opposite over adjacent, and the Pythagoras theorem for a right triangle gives you. So that's a standard, very simple geometrical properties in there. But these are 2 different ways of representing a vector in the sense that if I were to, in 2 dimensions, remember length and direction, right? So this is the length is A, hypotenuse, and that's your direction. Let me use Coulomb because we are going to have 2 different representations here. So this is is your magnitude of the vector. And that's direction of A. But there is another way of writing a vector. So notice this is a semicolon, and I'm going to use a normal comma separated list to have the another set of components. So this was say this is the x projection. Let's call it x naught. And the connection between them is notice in principle this vector, the way I write A1 and A2, it depends on its what is called the basis vectors. So its basis vectors are I and J, where I represents a direction in the x direction and J represents a direction in the y direction. And this is called the rectangular basis. And most of the index notation that we will talk about, remember there are only a set of rules, they are usually written in this notation. There is an implicit assumption that we are working in rectangular coordinates. You can take it to other coordinates also, but you should be very careful. It is possible. Remember, there are rules. As far as you know what those rules are, what are the basis for those rules, you should be able to extend it, but be very careful. Most of what we do is typically meant for rectangular columns. So instead of writing this, you say that most of the time I'm writing I hat and J hat, you get lazy. You say that I'm going to stop writing I hat and J hat, and I will just write A1 and A2. So that's how it begins. So let's so index notation now. Index is A1. Let's I can make this just for later purposes, I'm going to write this like this. It doesn't matter. But within a week or so, I'm going to define. Oh,
Sorry, I missed the part.
Yeah, no. So this is in our 2 dimensions. This is I hat and J hat. In 3 dimensions, it is I hat, J hat, and K hat. But this has this advantage that this easily generalizes to 1, 2, 3, or even 4 dimensions. 5 dimensions is immediately generalizer. And why did I write it on the top? That we will differentiate between what is a contravariant vector and covariant vector, but that will come in 2 weeks or so. But for the time being, it's just I, J, K. But you noticed I took about 30 seconds to write this, or maybe 15 seconds to write this. So you say time is precious, you want to, or you get lazy, either way you say that, oh, this you want to, so now this is not equal because you've really taken away some information. The basis vector information is gone in this. So basis vectors are implicit. And that's the biggest price you pay. Basis vectors often have lots of information in it, and it plays a significant role in quantum mechanics. Basis vectors are everything in there. And index notations are not the most convenient things when you're working in quantum mechanics. But again, remember that this is a set of rules. You can, if you know what you're doing, you can easily extend it first. But I said you're lazy, so you want to save time. So this is too much writing. This is too much writing, but this is also having a pattern. There's a A1, A2, A3. Why write this? So you get more lazy and you say that I'm just going to write I, right? And that's your index notation. And again, implicitly, you're saying that I is equal to 1, 2, 3. So I could be 1, I could be 2, I could be 3. So that's the simple idea of index notation. But now we do more than this. This is the beginning of it, but we of course try to do more. So how do we use this? So let's think of a scalar product. So that's the basis of not in the basis vectors. That's a foundation notation of index notation. Let's think of scalar product. So now I have vector A. And if I have vector A in rectangular coordinates, I have this components, 3 components, and immediately I have AI in my mind, right? So whenever I see a vector, I'm thinking there are 3 components, and these are the 3 components. If you have, and more explicitly, this will be A1, E1 plus A2, E2 plus A3, E3. And B, vector B is BI. And that's B1 plus E2, E2. We know how to add vectors, but let's talk about scalar product. A dotted with B. You're all familiar with this, but we want to introduce this index notation to deal with this. So A dotted with B. When you remember, these are rectangular bases, so these are orthogonal. These are I, J, and K. E1 is dotted with E2 is orthogonal, right? They're perpendicular to each other. So only the projections of one on itself contribute. So this is A1 times B1 plus A2 times B2 plus A3 times B3. It should be very clear. Most of you have used this sufficiently. So clearly there is a pattern here. The first term has an index of 1. The second term has 2 and 2 coming in. Third one has 3 and 3 coming in. You make that observation and write that as I is equal to 1 to 3. If it was higher dimension, it will easily go on, and you say this is AI. That should not be anything hard to see. Now, this is where it gets confusing. There is an implicit nature to this. Again, as I said, it's all about getting lazy. And you start seeing this all the time, and you drop the whole summation sign. And that's the major confusion, at least for first time when you see index notation being used. you say that you drop this whole thing and you simply write AI and BI. And you would argue, how is that possible? What about the summation sign? How do I know that I'm summing over or not? I've lost some information there. So this is called the notation. So this is called Einstein notation. Again, this is nothing deep. So Einstein is associated with it, but it is not really a big deal. It's Einstein notation. So what is the notation? How do I know that whether I have to sum it or not? If an index repeats, that means you have to sum it. If it repeats 3 times, you have made a mistake. Okay. If it is once, you don't sum. So if the index appears once, no sum. Twice, sum over. Thrice or more or greater than 2, look for mistake. Okay, so that's going to be your key. If an index repeats, so that is twice, this is called a dummy index. And this is just an index. I don't know whether it's given a name or not when it is not dummy, at least I don't know. Why is it called dummy? Notice this is, I went from here to that. The first equation did not have an I in it. So which means to say that when I went from here to there, if all of us were independently working on it, you might like a variable m more than I. So you might have written this as, let's say not even m, let's say n, right? You could have written this as n equal to 1 to 3. That's perfectly fine. Like, there's nothing wrong in there. And then you would say this is a n, bn. Notice these two are same. Right? And in that sense, this is dummy. Whenever it is summed over, it is dummy. If it is not summed over, you cannot do that. Okay, so we will see as very soon, almost the next example in the cross product, we will see that when it is not summed over, it has a meaning in the sense that the left hand side should have the same index as the right hand side. So we will see that in a minute. Is that clear? We will do one more thing. We can also write this as let's. Yeah, let's leave it like this. Okay. I wanted to introduce. Yeah, let me. No, I wanted. Sorry. Okay, so if you have a vector or the components of a vector, these are not the vector itself, these are the components of a vector AI. Notice I can write this as, now this is only one variable, this is not summed over. So this is having only one index, not summed over. But I can write this as a sum over, let's say, yeah. So this is sum over I is equal to 1, j. Sum over j equal to 1 to 3, and delta ij times aj. Now I've written an equation there. Remember, j is repeated now. I don't have to write the sum. So the equation takes the form I is equal to delta ij times aj. So what do I mean here? So let me do this better. So what I have done here is written an equation, like think of a matrix equation A1, A2, A3. A column vector, and then you have a matrix 1, 0, 0, 0, 1, 0, 0, 1. That's A1, A2, 3. Right. So when I think of a matrix equation, there are 3 equations, right? I'm saying A1 is equal to 1 times A1. So that's 1 times A1 plus 0 times A2, right? 0 times A2 plus 0 times A3. That's how I read it out. I want to have a notation. This is the first row and first column. This is the second row, second column, third row, third column. So this is going to be, I'm going to use the notation that this is 1, 1 times A1. Where delta 1, 1 is equal to 0. Maybe write that down. I've used a notation delta 1, 1 is equal to 1. The second row, first column is 0. Third row, first column is 0. Delta 1, 2 is 0. Delta 2, 2 is 1. Delta 3, 2 is 0. Delta 1, 3 is 0. 2, 3 is 0. This is just reading out that identity matrix, nothing big in there. So this can be written as 1, 2, A2 plus delta 1, 3 times A3.
3 3 3 equals to 1.
3, 3 is equal to 1. Thank you. Okay. Right. So using that, I can write this equation, almost a trivial equation here. A vector A is identity times that in terms of its components. So this will be the components of this matrix in that. So then use your index, summation notation, and you would say this is delta ij times aj. But now the summation is over j. And then you say, oh, no, this is 1, right? So 1. Right? And then you say, this is, oh, in using our notation, I drop the sum and say this is delta 1j times aj. So a1 is equal to delta 1j times j, right? So this is a short form of writing this. I mean, in this case, it is trivial because there's only one component in there. But imagine a situation where all 3 were contributing, then that's a simple short form. But this is not complete, right? There are 3 equations there. So this is A2 is equal to 2j times aj. The same thing can be repeated for 2. And the third component is A3 is 3j times aj. This is what, oh yeah, I know the word for that. I said no sum, this is called a free index. Remember, I called this a dummy index. When it is appearing only once, it is a free index. So this is a free index 1. It takes values 1, 2, 3. So if it's a free index, usually there are that many equations. I can choose it to be 1, I can choose it to be 2, I can choose it to be 3. So this is together written as AI is equal to delta ij times aj. So that's a equation written in index notation. If you were to write it in matrix notation, you would write this is a vector A is equal, this is an identity matrix, so you would say that's a matrix. If I were to use this notation for a matrix, we will come back to this. This is called a dyadic and dotted with the vector A itself. If you multiply an identity with a vector, you get back the vector itself. A trivial idea, but that's the essence of this. This piece here can be summarized as delta. So there are 9 rules there, right? I have given you a notation where there are 9 quantities specified. I can summarize them as delta ij. Is there a summation on this? No summation. I and j are free, so there are 2 free indices. When there is 0 free indices, usually it's a scalar. 1 free index, that's a vector. If there are 2 free indices, it's a tensor of rank 2. There could be 3 free indices, 4 free indices, 5 free indices, and so on. This is most commonly used in general relativity, where 4-dimensional space-time is very common, and we construct quantities where there are 4 tensors are very common. This is a second rank tensor because there are 2 free indices. So 2 free indices. But what is the rule here? This says that this is 1 if I is equal to j, and it is equal to 0 if I is not equal to j. That's a simple rule that I have specified for that matrix. It's basically the if you think of it as for intuition purposes, that's just the identity matrix, but in terms of indices, that is written in that form. This is a very useful quantity. It's called the Kronecker delta. Either you write it down or let's write it as delta. Like this is basically small delta, right? Delta symbol. And maybe so yeah, really comfortable. And yeah, there's one more thing I can say, that if you have A dotted with B, we earlier said this is the same as AI. BI. How many free indices in this quantity? 0. 0, right? Because it's a scalar. This is a dummy index, so there is no free indices there. But I can also write this as AI delta ij times bj. How many free indices in this? It's still no free index, there's 0 free indices, but there are 2 dummy indices in it. In this, there was 1 dummy index. This is 2 dummy indices, so that means there are 2 summation signs. This means that I am writing this as I is equal to 1 to 3, j is equal to 1 to 3. So the best thing is that whenever in confusion as to what an index notation means, bring back your summation sign. And after you do it for a couple of times, you will yourself become lazy and you say, okay, I don't want to write that. Then it's okay. But whenever you're not, oh, I don't understand what this means, just remember the index notation that double indices means that it's summation sign, and then there will be some clarity. In fact, write it explicitly. There's nothing wrong, and once you will write it explicitly, it is tedious. It will take you 3 lines to write that, but then you see the pattern. Oh, this is always happening, and that's exactly the point. said it's always happening, so I don't want to write it, so this is sufficient, the notation, does the job. Notice, whenever the Kronecker delta comes in, a summation eats away an index. So I have a I, so delta ij times C is A, just go to a different index. There is a summation here. This survives only when I is equal to K. This will always be equal to, so this is also called contraction. This is called contraction. So whatever is only, this works only with Kronecker delta. Whatever is summed over, you just drop it and give the free index to the free vector. It's that Ci. So that's a general tendency you will have, that whenever there is a Kronecker delta, you can contract that index and give that free index to the vector or a tensor that comes in. So learn that trick very quickly. So this is a trick, or this is an observation, a pattern. Yeah, I think I'll have to stop here. We are out of time. We want to do the same thing for vector product, and and your homework is mostly built out of quantities. We always work with normal vectors, but all your homework are situations where A1 and A2 and A3 are not normal numbers. They are operators. That means to say that you cannot swap them. Like 3 times 2. 3 times 2 is 2 times 3. But if I tell you that A times B minus B times A is not equal to 0, which is very common in quantum mechanics, they are operators. If they are not 0, then you cannot swap them. That's the only idea. And then index notation is very powerful. So you have to be careful with that. All your homework is based on that. But you need to have the vector product also. But whatever appears in dot product, you should be able to produce proceed. Probably there's only one question there with the dot product. Yeah. So but at least look into the homework so that you get some feel for it. Earlier lectures also help. So if you want to proceed with the homework faster, then you can go to last semester's, not last semester, last year's, 2 years back lectures, and that should be at least in this context, it should be a good representation of what it is. I'll stop here. Thank you.